Hello everyone, welcome to my lecture series of electromagnetic fields. We will discuss different theories, phenomena and numerical solution of different cases in this series. I hope this series will give a fruitful outcome to physics scholars or engineering students. In the previous part of this lecture series, we have seen the triple product of vectors. Press the I button on your screen to review that content. Today we are going to learn about Cartesian Coordinate System. So let us begin. So any coordinate system are used to locate any point, line, area, volume, any regular shape or irregular shape in the space. It has three axes named as x, y and z, which are mutually perpendicular. That means each pair of axes will make the right angle among themselves, and the common point or intersection point of these three axes is known as the origin of any Cartesian coordinate system. Cartesian coordinate system is also known as rectangular coordinate system. We will see why it is also called a rectangular system. So there are two types of Cartesian system, which are left-handed system and second one is right-handed system. So in both the system we will have three axes if we want to represent three-dimensional point or say volume, fine. But in both the types of system the selection of z-axis will be different. So how can we define left-handed system? So for that, first we will draw x and y axis at right angle. Then we will use the left hand and we will indicate the index finger in the direction of x-axis, and the middle finger of the left hand will be directed along the y-axis. Doing so, whatever the direction of your left thumb is indicating will be the direction of z, and any Cartesian coordinate system which is drawn by these rules using left hand is called left-handed system, while most commonly we all are using right-handed system. So how can we draw any right-handed Cartesian coordinate system? So again, first two steps will be same, that we will draw x and y axis at right angle. Then we will use our right, we will indicate the x-axis with a index finger of right hand, y-axis with the middle finger of the right hand, and at this moment whatever the direction that our right hand thumb is indicating will be the direction of z-axis. So you can verify in both the figures. So in first figure, left-handed system, the z-axis is going inward the screen, and in right-handed system for the same selection of x and y axis the z-axis is coming out from the screen. So as I said, the right-handed system is commonly used. However, it will make no difference in any calculation if you select the left-handed system for the calculation. Fine. Moving further, so why it is called rectangular coordinate system? Because any coordinate system will require some shapes, and intersection of those shapes will define a point or a line or a volume or a surface. Fine. So for Cartesian coordinate system we have taken three infinitely spread planes. Fine. We will discuss each three planes, that how does it moves around and how does it define a line and a point. Fine. So first plane that we are considering is this red one, which is spread infinitely and which will be always parallel to YZ plane. So if any plane is parallel to YZ plane, then such plane will be free to move along the x-axis. That means it can move from minus infinity to plus infinity on x-axis. So a plane of constant x which is parallel to YZ plane, and it is free to move anywhere on the x-axis from negative infinity to plus infinity. So depending on the position of this plane, if this plane is coming out from the screen, that is it will be in positive x direction, then its direction will be plus ax, and if it will move invert the screen, then its direction will be negative ax bar. Fine. But generally this plane is free to move from negative infinity to plus infinity on the x-axis, and by moving to such distance it can cover the every point of space. Fine. But here we are not able to locate any point with the help of just single plane. We are going to need more planes. So the second plane of our consideration is shown in as a blue parallelogram, which is always parallel to xz axis, as you can see, and being so the parallel to xz axis, it will be free to move from positive infinity to negative infinity on y axis. So its movement will be such translation in horizontal axis, that is y axis. So a plane of constant y which is parallel to xz plane, and it is free to move anywhere on y axis, that is from negative infinity to positive infinity, and the direction of this plane will be either plus ay bar. So if it is in the right hand portion from z axis, then its direction will be positive y. If it is in the left hand side portion from the z axis, then its direction will be negative ay bar, and it is free to move from minus infinity to plus infinity. Fine. Again, with the intersection of two such infinitely spreaded planes, we can have a line, but we cannot represent the point yet. So we are going to need one more plane. So this time we will consider again a which will be parallel to xy plane and free to move from minus infinity to plus infinity on the z axis. As you can see, this plane can travel along the z axis from negative infinity to positive infinity. So with the help of these three planes, we can represent any point, and the shape of these three planes are rectangle, and that is why this coordinate system is also called as rectangular coordinate system. Now let us learn how to represent a point in a Cartesian coordinate system. So a point can be represented in Cartesian coordinate system as, so first we need to decide which point I want to represent. So here for an instance I have taken some point P with x1, y1 and z1 as xy and z coordinate of the point. Then I will travel x1 distance from the origin. So origin is nothing but the intersection of three axes in the direction of x, because x1 is the point P. So traveling in such way, wherever I will reach, I have given that point name as A. Then in next step I will travel y1 distance, because the y coordinate of point P is y1, from the last point, and last point is nothing but A, in the direction of y axis, and wherever I will reach I will name it as point B. Then I will travel z1 distance, that is the z coordinate of point P, in the direction of z, and wherever I will reach is the position of point P, x1, y1 and z1. And a position vector of any point can be shown by drawing a vector from origin to that point. Here that point is P. So let us visualize how can we represent a point. So first we will draw a Cartesian coordinate system. So x and y axis I will draw in a perpendicular way. Then using right hand rule I will direct my index finger of right hand in the direction of x, the middle finger of the right hand in the direction of y, and at that point my thumb will indicate it outside. So this will be the direction of z. So we are trying to represent a three-dimensional system in two-dimensional screen or plane. Then what is our next step? So we will travel, first we will locate the origin, then we will travel x1 distance in the direction of x. So this point, that is A, it has the coordinate x1 0 0. Then we will travel from A to y1 distance in the direction of y. So here we will reach up to B point, which has a coordinate x1 y1 0. So this B point is on the xy plane, and from that point B we will travel z1 distance along the direction of z, and this point is nothing but p x1 y1 z1. So it is very easy representation, fine. And if we want to write the position vector of p, then what can we do? We will connect the origin with point p, and we can represent that vector ROP. R stands for position vector, so ROP. So this is the first way to represent any point in the Cartesian coordinate system, that you just travel along the axis depending on the coordinates of that point, fine. Another way to represent a point is quite messy, fine, but we will discuss the same. Now the same point p x1 y1 z1, p x1 y1 z1. If I want to represent the same point, then another method is to imagine our three surfaces at the origin. So xy plane, I have shown it in a navy blue color, xz plane I have shown it in a black color, and xy plane I have shown in the red color. So all these three planes are resting at 0, that is the intersection of these three planes are origin. So now what we will do, we will move the yz plane in the direction of x by the distance x1. Then we will move the zx plane in the direction of y up to y1. So the intersection of these two planes will give us a straight line, fine. See, both these planes are infinitely spanned, okay. So this line of intersection will also be infinitely long. Now we will move the final xy plane by the distance z1 in the direction of z, and intersection of this line and this plane, that is xy plane, will give us our point of interest, that is p x1 y1 z1. So this is another method to represent a point in Cartesian coordinate system by moving the planes representing the coordinates of the system. So moving, so the final position of yz plane will be x equals to x1, final position of zx plane will be y equal to y1, and final position of xy plane will be z equals to z1. So here we know that x, y and z of all these three planes are free to move from minus infinity to plus infinity, fine. So doing so, we can represent any point in the space wherever it lies. Then very important topic, which is called as base vector. So base vectors are unit vectors which are strictly oriented along the direction of the coordinate axis of given coordinate system. So for Cartesian coordinate system, the principal axes are x, y and z. So any unit vector which is laid along the direction of x, y and z, so such unit vectors are called the base vectors of the system. So here we have taken a right-handed coordinate system and defined a origin. So for such system, three unit vectors will be there which will represent the direction of x, y and z respectively, and all these three vectors are called the base vectors for Cartesian coordinate system, fine. Base vectors are actually used to represent any point in form of vectors. We will shortly learn how these are useful stuff for our study. Then position vector. We have a right-handed Cartesian coordinate system defined with the origin, and position vector of any point P can be defined as the distance of point P from the origin directed from origin to point P. So this is a very useful definition to be remembered for the exam point of view, that what is the position vector. One can easily represent the position vector mathematically with the help of their axis coordinates and base vector. So the application of base vectors is we can represent any point in the vector representation. So now the same way that we have moved the surfaces along the x, y and z direction, so in such way we will complete a parallelopiped, and the point P will be the upper corner of the parallelopiped, and if we connect the origin with the point P, then ROP bar will be the position vector of point P. Now we can represent this position vector by ROP bar is equals to x1, that is x coordinate of point P, multiplied by AX bar, which shows the x direction, plus y1, which is the y coordinate of point P, multiplied by AY bar, which shows the y direction, plus z1, here it will be z1, multiplied by AZ bar. So z1 is the coordinate of point z coordinate of point P, and AZ bar represents the z direction of the coordinate system. And doing so, if we can also find the magnitude of this position vector by under root x1 square plus y1 square plus z1 square. Actually, it is very easy to understand why this magnitude seems to be the under root of square of its x, y and z coordinates. Fine. Actually, we just need to apply the Pythagoras theorem twice. So first, just consider this xz plane. Fine. So this is nothing but the z1, this is nothing but the x1. Now the angle here will be 90 degree. So the hypotenuse of this parallelogram will give us two equal right angled triangles. Fine. And if we want to find the length of this line, then we can use the Pythagorean theorem, which says that the length of hypotenuse is the square root of addition of squares of base and height of that right angle triangle. So this white line will have the length under root x1 square plus z1 square. Fine. Now we can again see another right angle triangle which is formed with the base with this white line and height as y1, and the hypotenuse of this right angle triangle is nothing but the position vector. So the length of our position vector, that is modulus of ROP bar. So again we will apply the Pythagoras rule theorem, x1 square plus z1 square whole square plus y1 square. Now simplifying this term, we will get x1 square plus y1 square plus z1 square. So it is quite easy to prove that magnitude of any position vector is the square root of the squares of addition of the squares of its x, y and z coordinates. Fine. So it is common practice to present position vector of a point by that point itself. So either you can represent ROP bar, so it will give you the same meaning that this is the position vector of point P, or you can simply write P bar. So both these representation will have the same meaning at the time you are calculating any numerical. So here is a quick activity. So we are going to locate point P 1 2 3, point Q -1 5 -3, and point R 2 2 -2 in Cartesian space, and we will also find the magnitudes. So again, let us recall whatever we have seen. So any position vector can be represented in this way, and magnitude of that position vector can be calculated by this simple formula. Fine. So let us first locate the point P1 2 3. So P1 2 3, we will move 1 unit in the direction of x. So this is 1 unit. Then we will move 2 unit in the direction of y. So we will move 2 unit in the direction of y, and then we will move 3 units in the direction of z. So this is approximately 3 units in the direction of z. Now connecting now this point is P1 2 3, and connecting our origin with this point will be the position vector P. So position vector P, which can be also be represented by ROP bar, can be written as AX bar plus 2AY bar, because we have traveled 2 units in the direction of y, plus 3AZ bar, and magnitude of this position vector of point P will be under root, the x coordinate is 1, so 1 square, plus its y coordinate is 2, that's why 2 square, plus z coordinate is 3. So 9 plus 4 plus 1 will give you under root 14 units. Then if you need to locate or represent more than 2 points or many points in the same Cartesian coordinate system, then it is not necessary to draw such lines every time. Fine, you can remove it afterwards. Now let us try to represent point -1 plus 5 -3. So on x-axis I will move -1 unit. On y-axis I will travel plus 5 units. So this is my final point, and in negative z direction I will travel. So this inward direction is negative z direction. So in negative z direction I will travel 3 units. Fine. So this is my point Q -1 5 -3. Now joining a vector from origin to point Q and removing the unnecessary lines from our figure. So this is our final vector of interest, which is nothing but R O Q bar, or we can also say it simply Q bar. Fine. Again, Q bar can be written as -AX bar plus 5 AY bar minus 3 AZ bar, and magnitude of position vector of Q can be calculated by -1 square plus 5 square plus -3 square all under root. So it will be 25 under root 35 units. Now I left this third point R2 2 -2 on you to represent as a practice. Okay, moving further, the distance vector. Up till now we have learned how to represent a point and how to represent that point in a position vector form. Now we will learn how to represent a distance between 2 points. So consider 2 points P x1 y1 z1 and Q x2 y2 z2. That means both the points have different x, y and z coordinates. So arbitrarily I have shown a point P having the x, y and z coordinate and point Q having different x, y and z coordinates in a Cartesian coordinate system. Then the distance vector from point P to Q, fine, it is very important here to understand whatever I am saying. So the distance vector from point P to point Q can be represented as PQ bar, and which is nothing but the subtraction of position vector of Q and position vector of P. Fine. So PQ bar can be represented as the subtraction of x, y and z coordinates of 2 points in the direction of x, y and z respectively. So x2 minus x1 ax bar, y2 minus y1 ay bar plus z2 minus z1 az bar. Fine. Here it is very important to show the direction. Fine, because if I want to show the distance QP bar, then its magnitude will be same. Fine, but direction will be opposite. Fine. So always remember that whenever you are representing any distance vector, then coordinates of head will be plus and coordinates of tail will be subtracted from the coordinates of head. Okay, so this is very important point to remember while we are calculating the distance in Cartesian coordinate or any coordinate system. Once we have the vector representation of distance, then we can easily find the distance between 2 points as under root of x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. Now the same thing can be practiced in our previous example, as here we have the position vector of P and position vector of Q. Fine. If we want to find the distance vector from P to Q, then what can we do? So distance vector PQ is equals to Q bar minus P bar equals to, so Q bar, its x coordinate is -1 and P bar's x coordinate is +1, but here minus will be performed, so it will be -2 ax bar. Same way for y coordinate, we will have 5 minus 2, that is +3 ay bar. For z coordinate we have -3 minus 3, so -6 az bar. So this is nothing but the distance vector from P to Q, and if someone asks to find the distance between P and Q in such position, then the magnitude of this distance vector will be the distance between point P and Q. So it will be simply -2 square plus 3 square plus -6 square. So 36 plus 4, 40 and plus 9. So it will be under root 49, which is 7 units. Fine. So it is actually very easy to understand and calculate, provided you do not confuse between the actual calculation. Fine. So wherever you are going to represent a distance vector, you must subtract the coordinates of tail from the coordinates of head. Now unit vector. One may also ask to find a unit vector in the direction from P to Q. At that time we will first determine the distance vector, then we will calculate the magnitude of distance, and then we will simply take the division. So this will give you a unit vector in the direction from P to Q. Fine. So these three are the formulas which will be very helpful when we will solve the numericals. Once position vectors are known, then various mathematical operations can be easily performed in terms of component of vectors. Then very important thing to understand about any coordinate system is its differential element. So in order to understand any coordinate system deeply, one should understand its three differential elements, which are differential lengths, differential surfaces, and differential volume. We will learn each one of these in deep manner. So now consider a point P, X, Y, and Z in any Cartesian coordinate system, and then imagine that we travel a very small distance dx in the direction of x, very small distance dy in the direction of y, and very small distance dz in the direction of z. And doing so, we will reach to a new point which is very near to the initial point P, but it will have the coordinates as P prime x plus dx, y plus dy, and z plus dz. So this parallelepiped is called the differential element in Cartesian coordinate system, and this parallelepiped defines various things such as length, surface, and volume, which is going to be very useful when we will calculate any problem related to electromagnetics. So first thing to understand is differential length. So consider a point P, X, Y, Z and increase its each coordinate by a differential amount. Doing so, we will get a point P prime shifted from P having new coordinates as P prime x plus dx, y plus dy, and z plus dz. And this is the pictorial representation of the same. So this length by which we have traveled in principal axis direction are called differential lengths of the element. So differential vector length, or dl bar, is nothing but the position vector of final point minus position vector of initial point. So we will have x plus dx minus x ax bar plus y plus dy minus y ay bar plus z plus dz minus z az bar, and simplifying it, we will have dx ax bar dy ay bar plus dz az bar. So this is the differential length of this element, and the magnitude of differential vector length is nothing but under root dx square plus dy square plus dz square. Fine. Moving further to understand the differential surfaces. Here dx is differential length in x direction, dy is differential length in y direction, and dz is differential length in z direction. Now differential surfaces. So the point P is the intersection of three planes, while P prime is the intersection point of another three planes which are slightly displaced from the prior point. Now these 6 planes are called differential surfaces of element, and differential surfaces can be represented as a vector of area with its magnitude in and direction coming out from that surface. So in general, we have a formula of differential surface as ds bar is equals to ds, that is magnitude of that small surface, and an bar, that is unit vector normal to the direction of that surface. So let us understand how many differential surfaces are there in this element. So this differential element consists 6 surfaces, which can be shown as the front surface, that is this one, this surface is front, the right surface, that is this one, and the top surface. So first 3 surfaces are like this. In front surface, we can say the length of surface is dx. See, this length is dx, and this is the parallel to that length, so obviously this will be dx. This length is this is dz, and this height is dy, because the coordinate system that we have used is like this, x, y and z. Fine. So height of this front surface will be dy. Similarly, we can show the length of sides for right surface by dy height and dz depth, and top surface will have the length dx and depth dz. Its magnitude can be represented by a perpendicular vector coming out from the surface. So for front surface, the direction of area will be plus az bar. For right surface, the direction of the differential surface will be ax bar, and for top surface the direction will be ay bar. Now using the equation, or first we will see remaining three surfaces. So we have covered this top surface, right surface and front surface. The remaining surfaces are the back surface, that is this one, the left surface, that is this one, and the bottom surface, that is which is laying on xz plane. Fine. So another three surfaces are back, left and bottom surface. Total 6 differential surfaces are there in this element. Again, the length of each side of surfaces are very easy to determine, and the direction here, for the back surface the direction will be in negative z, for the left surface the direction will be negative x, and for bottom surface the direction will be negative y. So we have indicated the direction as well, and the formulas for 6 surfaces can be written as, so ds, z stands for the differential surfaces in the direction of positive z, so its magnitude will be dx into dy, because it's nothing but a rectangle. Fine. And the area of rectangle is its height and width, so height is dy and width is dx, so multiplication of dx and dy will give you the magnitude of this area. And what is the direction of this surface? So it is az bar. Similarly, for right hand surface, so we can represent it as dsx, that means the differential surface in the direction of positive x, so it will be dy dz, which is the magnitude of this surface, and ax bar is the direction of that surface, because you see the surface area is not a scalar quantity, but rather it is a vector quantity. And same way we can write the equations which for the remaining differential surface. So here dx minus z represents the differential surface in the direction of negative z, that is the back surface. So dx dy will be the magnitude of that area, and minus az, so this minus I have written in front, so minus az is the direction of this surface. Fine. See, whenever we will calculate some numericals, you will have the better understanding about differential surface, that how these concepts are useful. Fine. Because every time we will not come to the situation where regular shapes will be there. For irregular shape, many times we need to perform integration and differentiation. At that time, differential surface equations are very useful to reach up to the correct answer of the problem. If you have less understanding about differential surface, then it might lead you to the wrong answer. And the final topic of this video is differential volume. So point P is an intersection of 3 planes, while P prime is the intersection of 3 other planes which are slightly displaced from prior 3 planes. And these 6 planes together defines a volume, which is a rectangular parallelepiped. So you can see that these 6 planes are constituting a rectangular parallelepiped, and once a 3-dimensional volume is spanned in the space, we can define the volume of such parallelepiped as dV. dV stands for differential volume, equals to multiplication of all 3 differential lengths, that is dx, dy, dz. It will be also very helpful at the time of calculation. So thank you very much. Please post your queries or doubts in the comment box, and if you like my content, then do subscribe and like, share and comment. Thank you.